Good day everyone! In today's video, we're going to talk more about Laplace transform. So Laplace transform is very useful in field of science and technology as it replaces calculus operation with algebraic operation. Laplace transform has many basic properties, but in today's video, we're only going to focus on two theorems, which is the initial value and final value theorem. So these two theorems were given by French mathematician and physicist Pierre-Simon Laplace and is collectively called limiting theorem.
Good day to everyone. My name is Kyle Andre Salaras and I will be talking about Laplace transform initial theorem. So first we'll talk about Laplace transform initial theorem. In Laplace transform initial theorem we have two conditions to satisfy, which are: first, it is only applicable when ft is equals to 0 and t is less than 0. So when we say t is less than 0, this means from t equal to minus infinity to t equal to 0 minus ft must be equal to 0. The second condition is ft must not contain any impulse or higher order singularities at t equals to 0. When we say higher order singularities, it means it is a discontinuity. So when t is equal to 0, ft must not contain any impulse or discontinuities. So let's take one time domain signal ft, and let's say this signal is having the Laplace transform equal to fs, and the initial value of the signal ft. f0 plus will be equal to limit as s approaches to infinity, then the Laplace transform fs when multiplied to s. So, pwede natin ito gamitin ang initial value theorem if masatisfy natin ang conditions na ito. So, to prove this, if you remember the differentiation in time property of unilateral Laplace transform, we got differentiation of time domain signal ft raised to n. We will have the Laplace transform equal to s raised to the power of n multiplied to s, where fs is the Laplace transform of signal ft minus s raised to the power n minus 1 multiplied to f0 minus s raised to the power of n minus 2 multiplied to f dash 0 minus n, so on. Now, if n equals to 1, this means we are performing the differentiation of ft 1 times with respect to t. When we substitute n to 1, we will have dft over dt as the time domain signal, and its corresponding Laplace transform will be s raised to 1 fs. We will get fs minus s raised to 1 minus 1 equal to 0 s raised to 0 equals to 1 f 0 minus. So this indicates we are having a unilateral Laplace transform. So dft over dt is the input signal and unilateral Laplace transform is the output signal. Now we know our output is equals to sfs minus f0 minus equals to integration of 0 minus to infinity. The input is equals to dft over dt multiplied to the integral kernel, and we know in Laplace transform the integral kernel is equals to e raised to the power of negative st dt. Now we will break our integration into two different integrals. First, we will integrate from 0 minus to plus, then to 0 plus to infinity. So in this way, we have integration from 0 minus to 0 plus dft over dt e raised to the power of negative st dt plus integration from 0 plus to infinity dft over dt e raised to the power of negative st dt. Now we will understand what will happen to e raised to the power of negative st from 0 minus to 0 plus. We know 0 minus and 0 plus are very close to 0. So we can assume them to be equal to 0. And in this scenario, e raised to the power of negative st will become 1. So e raised to the power of negative st will become 1. Now, we will have integration from 0 minus to 0 plus dft over dt plus integration 0 plus to infinity dft over dt e raised to the power of negative st dt. The integration of dft over dt is equal to ft. So in the next step, we have ft as the result of integration from the first integral, and the range of integration is from 0 minus to 0 plus. And we will leave the second integral as it is. So this is what we have, and on the left side, we have sfs minus f0 minus. Now we can compare the right side. You will find minus f0 minus. So we can remove f0 minus, and we will have sfs equals to f0 plus integral of 0 plus to infinity dft over dt e raised to the power of negative st dt. Now we will have limit s approaching to infinity. Sfs is equals to f0 plus integral of 0 plus to infinity dft over dt limit s as approaching to infinity e raised to the power of negative st dt. In this part of the problem, we substitute s to infinity. So we will have 0. So this proves the initial value theorem. Now, I will give an example. ft is equals to e raised to 2 times t ut, and we will substitute t equals to 0. So we will have f0 is equals to e raised to 2 times 0 u times 0. So e raised to 2 times 0 is 1, so e raised to 1 is 1. So u times 0 is 0, so we will have 1. This function is for time domain. Now we will have another example for frequency domain. Fs is equals to 1 over s plus 2. So we will substitute s to 0 plus. So we will have limit s approaching to infinity s times 1 over s plus 2. So we can cancel out the s, then substitute the s with infinity, and we will get an answer of 1.
So the final value theorem determines the final value in time domain by applying only the zero frequency components to a system's frequency domain representation. The final value theorem is very useful for us in finding the final value of the function directly from its Laplace transform without the need for us to find its inverse Laplace transform. Now let's move on to the conditions which must be satisfied for us to be able to use the final value theorem. So the number one condition is that the function f of t and its derivative should be Laplace transformable. Second, the f of s has no fall on jw axis and right half plane where f of s is the Laplace transform of f of t. So the final value theorem states that if time domain signal f of t is having a Laplace transform equal to f of s, then limit as t approaches to infinity of f of t is equals to f of infinity, and f of infinity is equals to limit as s approaches to 0 of s times fs. So let's do a quick proof of this so we can understand where these theorems come from. We know that Laplace transform of f prime of t is equals to sf of s minus f of 0. And if you can recall the definition of Laplace transform, then you can rewrite the equation. Let's start in the left-hand side. First, we're going to write the e to the negative st and multiply it by the function itself, which is here the f prime of t, and then integrate it from 0 to infinity dt. In the right-hand side, we will leave it unchanged, so it is still sf of s minus f of 0. Next is, we are going to take the limit of both sides as s approaches to 0. And because there is no s in f prime of t and f of 0, the limit doesn't affect it, so now we only have this equation. And we can see here that if we take the limit as s approaches to 0 of e to negative st, it will result to 1. So if that's the case, we can simplify the equation as integral of 0 to infinity of f prime of t dt, and then copy the right-hand side of the equation. Next, we are going to evaluate the function at its two integral endpoints. So we have now f of infinity minus f of 0 equals limit as s approaches to 0, sf of s minus f of 0. We then cancel the f of 0 on both sides, and we end up now with the result that we are looking for, that f of infinity is equals to limit as s approaches to 0, sf of s. So let's now try to solve a problem. We have here f of s is equals to s plus 5 over s squared times s plus 9. Now, we have to find out the final value of the given equation, and according to the final value theorem, f of infinity is equals to limit as s approaches to 0 of sf of s. So now we are going to substitute the f of s value to the formula. Now, we have f of infinity is equals to limit as s approaches to 0 of s times s plus 5 over s squared times s plus 9. We're going to cancel the s, so we only have now f of infinity is equals to limit as s approaches to 0 of s plus 5 over s times s plus 9. Next is we need to apply the limit of the function. So we will substitute the s to 0. And then we have this, so 0 plus 5 is equals to 5, and 0 plus 9 is 9, multiplied by 0 is equals to 0. And now we have 5 over 0. And any number divided by 0 is always infinity, which means the final value of the function is infinity.